So far we have derived the solution for the wave, uh, which includes horizontal velocity, vertical velocity, and the pressure. And in all these solutions, you will see that we have two different terms. So first term is here, which is actually a function of z, right? Whereas the second term, which is more of a periodic term, that is a function of x and t, and that is how our velocity and all other pressure and vertical velocity as well are function of z and xt. So function of xt means this is and these are in periodic form, and that is why they keep changing in same pattern, whereas f of z, that you can see, is not really periodic. Okay, it has a fixed value at particular z. So whatever value we get at the top, that might be decreasing slowly as we go down. So to find the horizontal velocity or other parameters, we first need to find f of z, that is the maximum velocity, and based on that we define the periodic function, and also its decrease vertically. Okay, so as we go here, you see there is an example here that we are considering. This wave is moving this way. So the crest of the wave is moving with certain speed. Okay, and that speed is known as the phase speed. But at the same time, what happens is, when the wave is moving, that gives us the phase speed at the top of the layer, water layer. But as we go down from the water layer, like here, you can see the effects actually slowly decreases, right? So the effect that we have at the top is maximum, but as we go down, we slowly get a smaller and smaller effect of the wave, and as you go to the bottom, there is a chance that we get zero effect, and at the bottom we don't even feel the any sort of velocity. Okay, neither horizontal velocity nor vertical velocity, depending on the depth of the water layer. So there are two sort of functions happening here. One is the circulatory motion of the wave, which is happening at the top, and the water velocity we get at the top, that slowly decreases as we go down. Okay, and this part, what you see here, is defined. So what you see here is actually defined as a function of x and t. And what you see here is defined by function of f of z. Okay, so f of x and t, which is the periodic function either in cosine or sine, that tells you how your wave is moving from left to right or from one direction to other direction in space, that is x, and also how that is changing in time. But how the velocity is changing vertically in depth, that is given by f of z. Okay, and again, f of z is this particular part, and f of xt is this particular part, and same thing is applied in case of vertical velocity and pressure as well. Okay, and that is why this wave that we see here is not just a surface phenomena. It starts at the surface, but its effects are felt everywhere else as well, and that is how these two things are coupled, f of xt and also f of z. Okay, so now here we see that the crest is moving with certain speed, that is the topmost point of the wave, and everywhere else obviously we have certain velocity, which is obviously changing in periodic manner, where we have maximum velocity at the crest or at the trough, and the velocity in between is just between the maximum and minimum value. Okay, so here we see that in these functions that we have defined, f of xt is dependent on kx minus omega t, right? So f of xt basically depends on kx minus omega t, right? And that actually tells us the phase speed of the crest or of the wave. So here we will define, we'll take k out, this will become kx minus omega over kt. Okay, so we define a parameter called omega by k. This omega by k is known as c, that is the phase speed or the wave speed at the crest or trough. Okay, so this phase speed obviously depends on other parameters like the water depth, etc. So based on the equation that we have derived, that is the dispersion relation, which I can copy from here, we can try to find the relation between the phase speed and the depth. Okay, so if we divide this by k on both sides, we get c as plus minus g over k 10 hyperbolic of k h. Okay, so this is the phase speed we get as a function of depth, right? And you can see that depending on the depth, the phase speed will vary. So if you have some particular disturbance, right, created by, let's say, air turbulence or anything else, the wave speed that you can achieve will depend on the depth of the water layer as well as the k value. Okay, where k is just simply the wave number. All right, so that is the phase speed, and now we have another thing that is called maximum horizontal velocity, right? So at each point, so as we see here, velocity here is maximum at the top, and as we go down slowly decreases, right? So now let's see how this function is decreasing and what is its maximum value. So here we can try to analyze f of z for u x z t. Okay, so we will copy this particular parameter. So let's say that is u max is actually equal to u of z, as we have also considered that in the beginning, right? So this is the maximum horizontal velocity for the crest or trough, right? So when you have the crest, that time you experience the maximum horizontal velocity in positive direction or maximum horizontal velocity in negative direction when it is at trough, and anywhere in between you will have some value in between, right? And now this particular velocity that is felt at the top, that will slowly decrease down as we go from the top to bottom. So we are going to analyze both this thing c and also u of z, okay, for different type of waves that we observe in nature. So let's talk about type of waves that we have, and based on this type of waves we will try to find the value of c and value of the velocity and how does it decrease as we go down. So there are two kinds of waves you see here. One is called deep water waves, another one is shallow water waves. So deep water wave is something where the depth of the fluid is so large that the effects of water waves at the top is not felt at the bottom, whereas in shallow water waves the effects of the waves are also felt at the bottom. Okay, and there are different ways to define these deep water waves and shallow water waves, but in general we use h and lambda to define these waves. Okay, where what you see in the left is an example of deep water waves, where it is assumed that h is much greater than lambda, where remember that lambda is the wavelength of the wave and h is the layer depth. Okay, whereas in case of shallow water wave it is defined based on again h and lambda value, and it is assumed that lambda is actually greater than 20 h. So 20 looks like an arbitrary number, but based on different experiments this is found, and when wavelength of a wave is greater than 20 times of h, or h is smaller than lambda by 20, then the wave is considered to be a shallow water wave. And in these kind of waves you usually feel the effect of wave at the bottom as well, where wave is created at the top but effects are felt also at the bottom. Whereas in case of deep water wave the effects are generally not felt at the bottom. Okay, so these are two different kind of waves we have, and let's see how these equations that we derived are applied in these two cases. Okay, and just by looking at these two images you can see the left one is an example of maybe when you drop a stone in a lake, it creates a wave, but that lake is much deeper than the wavelength of these waves that are created. Whereas at the right side you see the waves near the beaches, where the wavelength is quite long compared to the depth of the water layer. In fact you can see the bottom surface of the layer, right? That means h value is much smaller than the lambda value. Whereas in left hand side image you cannot really see the depth of the layer, you can only see the waves. Okay, so now to be able to analyze these two type of waves better, we first understand these hyperbolic functions, right, which are there in these equations. We have hyperbolic functions, cos of hyperbolic cos, hyperbolic sine, and then again sin h here, cos h, sin h, etc. Right? So what we will do for these two different type of waves, we can actually simplify some of the forms so that we don't have to worry about using the value of z at different, or you know, finding different values of hyperbolic of cosine or sine, etc. For different values of z. Okay, so let's first understand this plot where you see cos h, sin h, and tan h, which tells you that if here you can assume x to be x equal to kh, because kh is something that we have in our equations. You can see kh is there here, right? In all other equations we have kh inside, and that's why we will try to study this particular problem in terms of x. So consider x is equal to kh. So if kh is much greater than 1, okay, that actually means that 10 hyperbolic of kh becomes equal to 1, right? That you see from this particular area. So this x is basically kh. So when kh gets really large, when this becomes greater than 1, your 10 hyperbolic is equal to 1. Okay, that is 10 hyperbolic curve that gives you a value of 1, and this value is basically, you can see that is 1 2 3 etc. All right, so that is the first consideration. Now if kh is much smaller than 1, that actually means that you're somewhere here, is when kh is much smaller than 1, that means that is close to 0, right? In that case you can see that 10 hyperbolic of kh is almost equal to kh, because there is a linear relation. It you can see it's like a straight line, and it behaves like a linear relation, right? And that's why 10 hyperbolic of kh is almost equal to kh, right? Now we will analyze sine hyperbolic. So in case of sine hyperbolic, you can see if kh is much smaller than 1, that again means that sine hyperbolic of kh is equal to kh, okay. If kh is much greater than 1, then sine hyperbolic of kh is also basically much greater than 1, that also becomes greater and greater, okay. Whereas in case of cos hyperbolic, if kh much smaller than 1, that is somewhere here, right? This tells us that cos hyperbolic of kh is almost equal to 1, right? That value you see somewhere here. When kh is almost equal to 0, your cos of hyperbolic is equal to 1, okay, or hyperbolic of cos, sorry. And if kh becomes much greater than 1, in that case you can see cos hyperbolic of kh becomes equal to sine hyperbolic of kh, right? That you see in this region. When kh is much greater than 1, cos hyperbolic becomes equal to sine hyperbolic, and same thing probably applies here. Instead of writing this equal to greater than 1, I think I should consider this to be equal to cos hyperbolic of kh, okay. So these are different functions we have, and these are different limits. If kh becomes much greater than 1 or much smaller than 1, what are the values? And now we are going to use these values in our solution. So starting with deep water waves, right, where we have got the wave speed to be equal to this, okay, let's use that little after some time. So in case of deep water wave, we know that h is much greater than lambda. That is something already defined, and we also know that lambda is equal to 2 pi over k, right? That is the definition. If you go back to the beginning, you will find out that k is 2 pi by lambda, or lambda is 2 pi by k. All right, so that actually gives you h is much greater than 2 pi by k, that actually means that hk is much greater than 2 pi, and hk is much greater than 2 pi, or let's write kh, which is something we have been using. That actually means that kh must be much greater than 1, right? If it is much greater than 2 pi, then that also means that it is much greater than 1. If kh is much greater than 1, then that actually means that if kh is much greater than 1, then 10 hyperbolic is equal to 1. This is something we already derived, and that's why this means that 10 hyperbolic of kh is equal to 1. That gives us value for c equal to plus minus g over k times 1, okay, which you can see is simply a function of wavelength or wave number, and not really okay. So this k is wave number, which we can also write as g lambda over 2 pi. Okay, so this is the wave speed or phase speed for deep water waves. And what do we see here is that your phase speed does not depend on h, right? C is not a function of h, right? And also c is proportional to lambda, okay? So you can see c does not depend on h, and that is because h is very large. So once we define a deep water waves, it does not matter how deep the water is, your wave speed will only depend on the wavelength, okay? And that is why in this kind of images, as you see here, once you throw a stone, in the beginning when the wavelength is smaller, wave speed or the crest will move slowly. But in these cases where you get the larger wavelength, the speed is also much greater, okay? So larger the wavelength, higher is the speed for deep water waves, okay? And that is actually what we get from this equation. So in deep water waves, we get higher wave speed for larger wavelength and smaller wave speed for a smaller wavelength, okay? So that is the behavior we see in case of deep water waves. And let's now analyze shallow water waves. Okay, so shallow water waves is something that we have defined as lambda greater than 20h. That actually means that lambda is much greater than h, right? And lambda here is defined as 2 pi by k is much greater than h. In other words, okay, kh is much smaller than 2 pi, which can also be considered or assumed to be equal to approximately kh is much smaller than 1, okay? So kh is much smaller than 1 in shallow water waves, and that is why here your 10 hyperbolic of kh is equal to kh itself, right? That is something we saw here. This one, if kh is much smaller than 1, then 10 hyperbolic of kh can be considered equal to kh. And that is why now when we consider the wave speed, we can simply write c to be plus minus g times k kh, and k here obviously cancels with each other, and your c becomes equal to plus minus gh. Okay, so now this is the phase speed for shallow water. Okay, in here you can see c is not a function of lambda, rather c is proportional to h to the power half. All right, so here it does not matter what is the wavelength, your wave speed will only depend on the depth, and here you can see the velocity decreases, and that is what happens in this case. As depth decreases, velocity slowly decreases, and this is many times you see in case of beaches when water waves comes with certain speed or with higher speed from far, but as it approaches the shore its velocity decreases, and it actually completely calms down as it reaches the shore, right? So that is because your edge becomes very small as it approaches the shore. Okay, so we have got these relations for the phase speed in form of lambda or h, and here is what when we try to plot it against lambda by h, we get this kind of plot. So we have got these two relations which we will copy. So this is for deep water wave, and this one is for shallow water wave, right? And we are trying to plot it against GH. So we will do C over GH, that becomes, and I'll simply remove the T square H square. So I remove the plus minus sign from here, and okay, I think it does not have to be squared because that's already this becomes equal to 1. Right, so here C or GH is so this value actually what we have plotted is simply depends on the lambda, whereas C by GH square root is a constant, and that is what you see in this region. C over GH depends on this value for different values of lambda by H, whereas H increases and lambda by H increases, your C over GH becomes constant, that is almost equal to 1. Okay, so this is the relation we get between phase speed versus depth, where with you can see the H is in denominator. So with shallow water we get, so you can in fact say this is shallow water to deep water. Okay, the phase speed goes from 1 to a smaller close to 0, or not really the phase speed but phase speed divided by GH. Okay, so this is the relation we have got for phase speed, but now we still have another parameter, that is the horizontal velocity, right? And horizontal velocity, as we have seen, actually decreases from, its effect decreases from this maximum value here till towards the minimum value at the bottom. So let's now try to analyze the horizontal velocity, right? And horizontal velocity, we particularly are trying to analyze this term. So let's go ahead and so here again we are trying to do it for shallow water and deep water. So in case of deep water waves, we already have seen that KH is much smaller than 1. That is uh, this one, KH is much greater than 1, sorry. Right, if KH is much greater than 1, we know that sine of KH is almost equal to cos hyperbolic of KH. Okay, that actually means that for Z equal to H, cos hyperbolic of KZ will be equal to sine hyperbolic of KH, right? Or in other words, let's do it in two steps. Cos of hyperbolic of KH is equal to this, right? So when we put Z equal to H, our cos hyperbolic of KZ becomes cos hyperbolic of KH, and that actually is same as this, and this is coming from here, right? But for when Z is equal to 0, that actually means that cos hyperbolic of 0 is equal to 1. Okay, so now let's analyze this u max that we have. U at Z equal to H gives us a omega sine hyperbolic of KH over sine hyperbolic of KH, where this one is coming from cos hyperbolic of KZ, right, as we have already proved here. So that is the same thing happening here. So that actually means that u at Z equal to H is equal to simply a omega, right? Whereas when u at Z equal to 0 gives you a omega 1 over sine hyperbolic of KH, right, which we know that when KH is much greater than 1, that is here, this blue region, when KH is much greater than 1, your sine hyperbolic of KH is also much greater than 1, right? So I can also copy this figure. Sine hyperbolic of KH is much greater than 1 for KH much greater than 1. Okay, that actually means that u of Z equal to 0 is much smaller than u of z equal to h, right? Because in case of u of, or in other words, what we can do here is u of z equal to 0 over u of z equal to h. If we divide it, a omega cancel out, and what we get here is 1 over sine hyperbolic of kh, right? Where sine hyperbolic of kh is much greater than 1. That actually means that this value is much smaller than 1. Okay, so this indicates that the velocity decreases to a negligible value at the surface in case of a deep water wave. Okay, so what actually it means is, when there is large wave at the top or high velocity at the top, if it is deep water wave, your velocity at the bottom will be negligible, it will be almost zero. In deeper the layer, the effects will be smaller. Okay, this is what we get for deep water wave. And now let's try to analyze this case for shallow water wave. Okay, and in case of shallow water wave, we know that kh is much smaller than 1. Okay, and that is why we go back to this particular equation here. Okay, and now we apply at z equal to 0, or let's start with z equal to h. kh is much smaller than 1. That actually means that sine hyperbolic of kh is almost equal to kh, right? And also cos hyperbolic of kh is equal to 1. Okay, when kh is much smaller than 1. All right, so u at z equal to h means this is a omega or 1 over kh. Okay, so a omega over kh. This is the speed we get for z equal to h. When z is equal to 0, that means that cos hyperbolic of 0 is anyway equal to 1. Okay, and also sine hyperbolic of kh is already equal to kh. So what do we get here is that u of z equal to 0 is also 1 over kh. Okay, so a omega over kh. So basically u at z equal to 0 over u at z equal to h are same. Both we get, so this is at z equal to 0 and this is at z equal to h, and that is equal to 1. That actually means that u at z equal to 0 is equal to u at z equal to capital H. So what actually it means is, the velocity that you have in the wave at the top is same that is felt at the bottom, right? So wave speed at the bottom is same or sorry, I should not really use wave speed, I should say fluid speed at the bottom is same as the wave speed at the top, right? And this actually leads into all sort of surface related phenomena, like let's say there is deposition or erosion of surface material. So this leads into erosion of surface materials. Okay, so this happens in case of, this is a case of shallow water wave where the velocity at all points remain the same. So basically u of z is basically simply equal to u, that is constant and does not depend much on the z coordinate. Okay, so surface water waves actually impacts coastal region very badly, because in coastal region your depth, layer depth is very small, and that is why water velocity that is there at the wave at the top is equally felt at the bottom, right? And that is what you see in this kind of flows. These are basically images from the tsunami, right, where this is also a sort of water wave, and that is why water velocity we have at the top is there at the bottom as well, and that is why it tries to drag everything that's at the bottom. Let's say if there is tsunami that is going over over the buildings or other things, it just tries to drag the buildings or cars or whatever come on its way, right? And that's why tsunami or these kind of waves are extremely destructive, because these come under the category of shallow water wave. Okay, these come under the category of shallow water waves. Okay, because they try to have the same velocity at all points. All right, so these are different type of waves we have seen. In case of deep water wave, the maximum velocity at the top is different from at the bottom. At the bottom we see almost zero maximum velocity, but in case of shallow water wave we have almost the same velocity at all points, and that's why the shallow water waves are much more destructive in case of waves like tsunami. Maybe not always, but in this kind of waves which have really large amplitude, etc. Okay, so here we conclude our lecture for water waves. And in this case, to quickly rewind, we studied just one kind of waves, which is surface gravity waves, but there are other type of waves like internal gravity wave or topographic waves. But given the constraint we have in terms of time, we are able to only consider surface gravity waves but not other waves. However, having seen the basics of surface gravity waves, it will also be possible for you to explore the basics of internal gravity waves or topographic waves, etc. on your own. Okay, so we conclude the waves part, and we will go to the next topic in the next lecture.